In this video, we are going to continue talking about relative extrema and critical numbers. So if we remember from our last video, a critical number, those are places where our derivative is 0 or where that derivative does not exist. All right, so those are the critical numbers. The values x, the value x. In order for it to be a critical number, it needs to be in the domain of the function. So you might need to check that. There might be places where that derivative does not exist, but the value wasn't in the function, in the domain of the function to begin with. So, all right. If f has a, we have this theorem, if f has a relative minimum or a relative maximum at x equals c, then c is a critical number. That tells us if we are at a maximum or minimum, then it must be the case that the derivative is 0 or the derivative does not exist. Now be careful. This does not mean that all critical numbers are relative extrema. Right? That is not the case. So the only possible places we could have relative extrema is at critical numbers. We only need to check critical numbers, but just because it's a critical number does not make it a maximum or minimum. Right? You can have places, things like this that will happen, where you can have a graph that kind of flattens out. Our derivative right there is 0, but this is neither a relative max nor min. Our derivative here is 0. But we don't have a maximum or minimum. All right, so let's take some time and let's practice finding critical numbers. All right, so here we have find all critical numbers of the following functions. So f of x is 2x cubed plus 9x squared plus 12x minus 1. Then our derivative is going to be 6x squared plus 18x plus 12. What are we going to do with those derivatives? Well, we are going to find where does that derivative equal 0? So we have 6x squared plus 18x plus 12 equals 0. We can factor 6 out, so we have 6 times x squared plus 3x plus 2. And that factors further to x plus 2 times x plus 1. So x is -2 or -1. We should also check where this derivative does not exist. And this function does not have anywhere where the derivative does not exist. It's a polynomial, and for polynomials, our derivatives all exist. So the only critical numbers we have are -2 and -1. Excellent. All right, let's look at another example. Here we have g of t is equal to t times the square root of 9 minus t. And we are only defining this function for values of t smaller than 8. So we don't need to worry about values of t larger than 8. Let's take our derivative. We're going to have to use a product rule. So we have the derivative of the first. So the derivative of t is just 1 times the second plus the first times the derivative of the second. So we'll have 1/2 9 minus t to the negative 1/2. We have a chain rule that's going to happen there. We need to multiply this by the derivative of the inside. Our inside has a derivative that's equal to -1. And so we have the square root of 9 minus t minus t over 2 square root of 9 minus t. And that 9 minus t in the second one, that is in the denominator because its power is -1/2. We're going to set this equal to 0, but if we're going to do that, we should first get a common denominator between these two pieces. So if we were to multiply that first piece by 2 root 9 minus t over 2 root 9 minus t, then we are going to get 18 minus 3t over 2 root 9 minus t. Great. What are we going to do with that derivative? Now we're trying to find critical numbers, right? We're finding critical numbers. So to find those critical numbers, we are going to set this derivative equal to 0. So the top stuff will be equal to 0, which would tell us that 18 is equal to 3t, and t is equal to 6. So we're going to have a critical number at 6. We should also check where the derivative does not exist. That's going to not exist when the denominator is 0. It's also going to not exist whenever the stuff underneath that square root is a negative. So when it's equal to 0, or whenever it is the stuff under the square root is smaller than 0. So everywhere that t is greater than or equal to 0, that derivative is going to not exist. Sorry, everywhere where t is greater than or equal to 9, that derivative is going to not exist. But our original function, we are only restricting it to values smaller than 8. So all of those points are not going to be critical numbers. In fact, most of them, even if we didn't make that restriction, most of them wouldn't have been in the domain anyway. Anything that was 9 or greater, anything that was greater than 9, at 9, that is in the domain of the original function. So that would have been a critical value. But as is, 6 is our only critical value. Great. Come back for our next video, and we are going to look at not local or relative extrema, but we are going to look at absolute extrema. We will see you there.